So in this video, we're going to take a look at binary addition in more detail and introduce a new kind of binary value that's going to help us out with various arithmetic operations. But before we get there, let's take a look at how binary addition actually works using the format that we already have been using throughout the course, which is unsigned binary numbers. In this scheme, what I mean by unsigned numbers is that every binary value is positive. I have no way of representing a negative value in binary with everything that we've discussed up until this point. And under this particular scheme, if we want to add two binary numbers together, it's actually set up in a circular fashion. So if I want to add 8 plus 6, for example, I can start here at 8 on the wheel and just count up 6 more places going clockwise. So 1, 2, 3, 4, 5, 6, and I end up at 14, right? But notice what happens when we go all the way around, when we complete a full lap of this particular circle. For example, if I want to add 13 plus 5, I again can use that same mechanism, 1, 2, 3, 4, 5, but I end up at 2. We know that 13 plus 5 should be 18, but there's a problem with this operation that I've requested. I'm limited to 4 bits in this particular example, and there's no possible way to represent 18 using only 4 binary bits. So I have no way to represent the answer to the problem that I've requested. And what ends up actually happening is that once I get to the largest possible binary value that I can possibly have, I flip back around to the smallest possible binary value, and I keep going on as if nothing wrong is happening at all. And I end up with the binary value of 3. Right? I end up with this value of 3. Now you'll notice that 3 is actually the result of 18 modulo 15. So 15 is the largest possible binary value that we can actually create. 18 mod 15, well, 15 goes into 18 once, and there is 3 left over. So this 3 actually represents the modulus of the answer that we want as it relates to the largest possible binary value that we can represent with the amount of bits that we have. When this occurs in an actual machine, this is what's called an overflow. We have overflowed the number of bits that we have, and we've wrapped around back to the smallest value. Notice that if you were going to do subtraction, if I were to say 3 minus 5, for example, and work counterclockwise, 1, 2, 3, 4, 5, I'd end up with 14, right? Again, I wrapped around from, this time from the smallest value to the largest value. This is still called an overflow. It is not called an underflow. An underflow is something completely different that we will talk about at some point in the future. So anytime I wrap around, either from the largest to the smallest or the smallest to the largest, that's what's known as an overflow. I've exceeded the number of bits of information that I am able to use to represent the number that I need. The reason that I bring this situation up is because we're about to introduce a class of binary values that allows us to represent negative as well as positive values. Negative numbers are extremely useful, of course, and we would like to have a way to represent them. And so, under such a scheme that might look something like this, where you see I've got negative values as well as positive values on this circle, right? This just makes this issue of overflow a little bit more complicated, a little bit different. So we can see now that when I go from the lowest, or I guess what in our previous scheme was the largest binary value, all ones, we can see that under this particular scheme it represents a negative 1. So going from that to 0 actually makes a whole lot of sense. The overflow condition is actually now changed down here. We see that now if I want to go from positive 7 and count up 1 more, right? That's actually going to take me to a value of negative 8. So my overflow has switched from this position on the circle over here to this position on the circle over here based on the way that we've set up these binary numbers to represent negative values. So let's take a little bit more time to talk about what a negative binary value actually looks like. You may notice that all of the negative values that are represented in this particular slide start with the value of 1. And that's not a coincidence. all of the positive values start with a and 0, which is neither positive nor negative, start with a binary 0 in their first bit. So if we want to represent negative as well as positive values, we use this first bit as a sign bit. If the sign bit is a 1, that means we're dealing with a negative value. If the sign bit is a 0, that means we're dealing with a positive value or potentially 0. Not only that, but we use a special version of representing numbers called 2's complement to determine what a negative value is related to its corresponding positive value. And let me show you a couple examples of how that actually works. Let's say I give you this 4-bit value here, 0, 1, 0, 1. The 0 indicates that it's a positive value, right? This is the 4's place, this is the 1's place, so this is a positive value 5. Let's say I want this to be a negative value 5 instead. Well, the way that I'm going to convert this to be a negative 5, it would be nice if I could simply switch the sign bit from a 0 to a 1. But that's actually not going to be negative 5 under this particular scheme. It's not going to work out that way. What we're going to do instead is we're going to flip all of the bits. So if it's a 1, it's going to become a 0. If it's a 0, it's going to become a 1. And then we're going to add a 1 to the result of that. So flipping all of the bits gives us 1, 0, 1, 0. Adding a 1 to that result gets us 1, 0, 1, 1. So to represent negative 5 using 2's complement form, we end up with 1, 0, 1, 1. So this is positive 5. And this is negative 5. We can see that the sign bit is a 1, indicating that it's negative. Here, the sign bit is a 0, indicating that it's positive. Right? So what is the reason for this? Why can't I simply switch the sign bit to get from positive to negative? Well, there's a very important reason for this, which the Zybic covers in a lot more detail than I'm going to cover in this video. The short answer is that it makes it a lot easier for us from the perspective of designing digital circuits to represent these binary values using what's known as 2's complement, which is what I just went through with you. Notice that it works in both directions. Let's say I start with a negative 5 and I want to go back to a positive 5. I can run that same process in reverse. I'm going to flip all of the bits, so it's going to become 0, 1, 0, 0, and then I'm going to add a 1 to that result, so I get 0, 1, 0, 1, which is my positive 5. Or another way that you can do this, another trick for converting things from positive to negative values, right, is the following. Find the rightmost one and leave that bit alone. So here, this is the rightmost one. I'm not going to do anything to that. I'm going to leave it where it is, and I'm going to flip all of the bits that come to the left of it. Right? So this is going to remain the same. This will become 1, 0, 1, so the result will be 1, 0, 1, 1. Again, this also works in reverse, right? So find the rightmost 1 bit, that's this bit here, and flip everything to the left. That will bring me back to my positive 5 value. So in the next video, we'll actually see how we can use these 2's complement values to create efficient logic circuits for performing other arithmetic operations.